Posso fazer?
Vamos, Marcelo. Vamos. Boa tarde a todas e todos. Hoje nos acompanha em nosso seminário o professor Marcelo Avena. O professor Marcelo é professor titular na Universidad Nacional del Sur, na cidade de Bahia Blanca, que fica no sur da província de Buenos Aires. Certo? O Marcelo fez seu doutorado na Universidad Nacional de Córdoba, na Faculdade de Ciências Químicas, e posteriormente fez o pós-doutorado na Universidade de Wageningen, na Holanda, e também realizou outro pós-doutorado na Universidade de Genebra, na Suíça. Então, respeito de seus números, certo? Eu tenho um H41 e mais de 5.900 citações, com alguns trabalhos, inclusive trabalhos feitos 100% na Argentina, com um elevado número de citações. Ou seja, que isso é simplesmente para falar que o trabalho que faz é bastante importante. Então, bom, o título do seminário está na tela e vocês vão ver mais detalhadamente um pouco a especialidade dele e tudo isso, na medida que ele vá dando a sua conferência. Então, muito obrigado, Marcelo, por ter aceito participar de nossos seminários e pode começar.
Thank you very much, Roberto, for this kind introduction. In these pandemic times, well, it's really nice to have internet and to have Google Meet and to have Zoom, because we can give seminars and conferences without the need of traveling. So this is quite good. Thank you for inviting me, and this is a good way for me to tell you what we are doing in Bahia Blanca in Argentina about surface chemistry, about our research. So, as the title of the presentation says, we are going to talk about the reactivity of the metal oxide and mineral water interfaces. And since I'm an inorganic chemistry professor and we do surface chemistry, interfacial chemistry, so I'm going to combine both disciplines, inorganic chemistry and surface or interfacial chemistry. In Bahia Blanca, this is the outline of my presentation. At the beginning, chemistry, I will make a brief introduction, making analysis between. So, as the title of the presentation says, metal ions in solution, we are going to talk about the reactivity of the metal oxide and mineral water stress on reactivity. And since I'm an inorganic chemistry professor, reaction mechanism, we do so we are going to surface chemistry, interfacial chemistry. So I'm going to link. Then I'm going to combine. I will show you the experiments we do. We have work in this part of our topic, of our work with infrared spectroscopy. So we have done ATR, FTIR spectroscopy. Then I'm going to speak something about the modeling. This is a very classical and simple model just to handle the experimental data and to obtain rate parameters when we do adsorption kinetics. And the main examples we are going to see today is phosphate adsorption and how we get the adsorption rate coefficients with this setup, with this experimental setup. And then something that is we are very interested on is the glyphosate, the surface chemistry of minerals and the adsorption, desorption of glyphosate.
Acaba de comenzar.
Of this side, and we're going to see something and to learn something about the desorption mechanism of glyphosate from this mineral, from this goethite. So, since we do surface chemistry, we are speaking mainly about adsorption, desorption processes. So, we are going to speak a lot about adsorption, desorption in this talk. At the end, if we have some time, I'm going to speak something about materials and minerals that we are using as materials just to purify aqueous solutions and to decontaminate aqueous solutions. So we start now with the introduction. And to understand the reactivity of the mineral surface, it is very instructive to make an analogy with the reactivity of dissolved metal ions in aqueous solution. We are going to see that the reactivity of a metal ion in solution is very similar to the reactivity of a metal ion at the surface. So let's make this analogy. This slide here is very basic. This is general chemistry. This is basic inorganic chemistry, but it's going to be very useful for us. It's crucial for us for understanding what comes next. So when we write in a chemical equation and we represent a metal ion, we usually write it down like this. For example, in this case, iron 3 aqueous, just to say that this iron 3 ion is dissolved in an aqueous solution. But the real species here is this one, is a complex, is a coordination compound where this iron 3 ions is directly coordinated, is bonded to 6 water molecules in this case. The 6 water molecules are the 6 ligands that are directly bonded to the cation iron 3, and this is what we call in inorganic chemistry, and you may know, of course, a complex, a metal complex, or a coordination compound. If we see this complex in 3 dimensions, we have this figure, the central cations iron 3 is here, and is coordinated, directly bonded to 6 water molecules. These are called the ligands. We have the central cation. Now, if we connect these lines, the positions here with lines, or the position of the ligands, we get a geometrical figure. This geometrical figure here, this is an octahedron, and this is why this is called an octahedral complex. Yeah, this is an octahedron. I want you to remember this figure here because it's going to be necessary for the next slide. And then, well, in the center of the octahedron, we have the cation, and in the vertices, we have the 6 ligands. This is a complex where iron 3 is hexa-coordinated. This is another way, is a simple way of representing it with the central cation here and the 6 ligands, and we are going to use also this representation later. So how are iron 3 ions, for example, at the surface of a mineral? We're going to see that metal ions are also forming complexes, are also forming coordination compounds within the mineral structure and at the surface of this mineral. This is a schematic representation of a solid, of a mineral. This alpha iron octohydroxide is the name of the mineral is goethite. It's very commonly found in soils and sediments in nature. It's found everywhere, is what gives the red color to soils, for example. And, well, it's very active in soils, and we are studying it. So this is a representation, the small spheres, let's see, the yellow or the light brown spheres here represent iron 3 cations, and the red spheres are oxygens ions or hydroxyls ions. What happens if we connect all red spheres with lines? We get this. We get all octahedral complexes. And what we see here is that iron 3 is everywhere in this mineral, inside the particle or at the surface, is always forming part of octahedral complexes with iron 3 in the center. I have the zoom here, I have enlarged here the surface. Just assume that this is the surface of this solid particle, and this surface is in contact with water, with an aqueous solution. We have the surface here. I left just intentionally one octahedral without drawing, just to see that we have iron 3 in the center of the octahedron, and we have the 6 ligands surrounding the central cation. So this is the case where we see that iron 3 at the surface of a mineral, at the surface of a metal oxide, is very similar to iron 3. I go backwards to iron 3 in solution. They are just forming complexes, they are very similar, and so we should expect that they participate in the same kind of reaction at the surface here or in solution. One of the most important reactions of metal complexes, of coordination compounds, is this one. This is a ligand exchange reaction or ligand substitution reaction. Is a key reaction for complexes, and in solution is well known this kind of reaction. We have the metal complex, and it reacts with an entering ligand. This ligand is going to replace one of the ligands here, this one. Let me see. Oh, sorry. This one here. Yeah, this is called the leaving ligand because it's going out, and this is being replaced by this one that is the entering ligand. So in this reaction, we have a ligand exchange or ligand substitution. We can substitute 1, 2, or 3. We can substitute all of these ligands if we want, but the simplest reaction is just substituting one of them. So this is well known in solution. And what happened at the surface of a mineral or a metal oxide? We have the same kind of reaction. Just assume that we have the surface of a mineral here, the complex here with this iron 3 cation and a hydroxyl ion acting as a ligand. If we are in the aqueous solution and we have a solution of an entering ligand, this entering ligand can substitute this hydroxyl ion just to have this as a product of the reaction. And what we see here is that after the reaction took place, this entering ligand became absorbed at the surface of the oxide, and the hydroxyl ion just went out to the bulk of the solution. So ligand exchange, this ligand exchange or ligand substitution reaction that occurs in solution also occurs at the surface of mineral particles, and this kind of reaction leads to absorption of anions in these cases, or absorption also of neutral molecules, or absorption of cations. So ligand exchange reactions are very important for desorption reactions at mineral and metal oxide surfaces or interfaces. We are interested usually in environmental chemistry, so that's why we study minerals and metal oxide surfaces, and we study also dissolved ions or molecules that are environmentally relevant. For example, phosphate. Phosphate is a very good ligand that can absorb at the mineral surface. It is a very good ligand, very good electron donor, so we can attach to the surface. We are also very interested in glyphosate, this herbicide. Glyphosate here has a phosphonate group, so it works similarly as the phosphate. It can bind the surface quite strongly. We are also interested in other ligands like arsenate and chloride, carbonate, sulfate, etc. Everything that can be in nature, and also some polymeric molecules like this fulvic acid or humic acid. These are, well, the organic matter, soil organic matter, or in sediments, in lake sediments or oceanic sediments. This is mainly the organic matter. These molecules have a lot of carboxylate group that they are good ligands, so they attach quite strongly to the surface of minerals. We are interested nowadays in the mechanism of ligand exchange at the surface. And there are two limiting cases for this mechanism. The mechanism in solution is very well known. They have been studied for, 40 or 50 years. So since the 70s or the 80s, these mechanisms are known in solution. Nothing is known at the surface. We have two limiting cases in solution. I'm going to speak of what happened in solution. Two limiting cases. One of them is called dissociative substitution, this D mechanism, dissociative. And we have also the associative substitution, the A mechanism. This is the same reaction, but the mechanism is the same. The products are the same, but the mechanism, is different. In dissociative substitution, we have a first step where this ligand, the living ligand, leaves first, we get an intermediate, a penta-coordinated intermediate. Just when this living ligand leaves the complex, it has a free space here. So in the second step, the entering ligand is attaching the metal ion to keep the proton. This is the rate determining step here. In the associative substitution, this is the other way around. We have the metal complex, the entering ligand enter first in the first step, so we get an intermediate hepta-coordinated coordination number 7 here. It's as an intermediate, and then in the second step, the living ligand leaves the complex just to keep the reaction proton. And this is the rate determining step. So look at here. In this case, the entering ligand is not participating in the rate determining step. And in this case, the entering ligand is participating in the rate determining step. So this is going to give us a good tool to differentiate between dissociative substitution and associative substitution. Then we're coming back to this when we start studying the surfaces, just to see if our mechanism is a D mechanism or an A mechanism. Which are the main experiments we have done for this kind of studies? We have done absorption, desorption, kinetics, and we have used quite a lot infrared spectroscopy, ATR, FTIR spectroscopy with this cell. I think you may know how it works. This is the sensitive crystal, the ATR crystal. On top of the crystal, we make a film, a layer of our particles, for example, a goethite film here on top of the crystal. And so by infrared, we can detect the signal of this film, and we start flowing a solution. Just suppose that we start flowing a solution of glyphosate or a solution of phosphate. Phosphate and glyphosate start to absorb on the surface of the particles here in this film, and infrared is detecting the signal of these adsorbed molecules, of these adsorbed ions, and we can register the spectra in infrared and to follow the reaction. So in this way, at the beginning, we are going to see adsorption. So we are getting an increase in the signal, in the infrared signal, just telling us that we are having adsorption. And then if we want to desorb, the only thing we can do, the simplest thing we do is just start flowing a desorbing solution. For example, water, or changing the pH, or changing temperature, just to make phosphate or glyphosate to desorb from goethite, and we can register that as a function of time with infrared. With this kind of cell, it's very nice because we can control pH, we can control temperature, ionic strength, adsorbate concentration, flow rates, and many other things. So now I'm going to give some example of what we can get with this kind of experimental setup. This is an example for phosphate adsorption, desorption from goethite. This is the infrared signal. We are just registering the spectrum of adsorbed phosphate as a function of time. This is the first spectrum after 2 minutes of adsorption, 4 minutes, 6 minutes, 8 minutes, 10 minutes, etc. So we can plot here the absorbance, here or here the absorbance as a function of time, or we can convert absorbance, infrared absorbance, to adsorbed amount of phosphate. For example, in this case, this is micromole per square meter of goethite. We can convert this data to absorption data and plot. The symbols here are experimental data, and plot adsorbed amount as a function of time. So you can see that with infrared spectroscopy, we can have a really nice adsorption kinetic curve. And then, in this case, we have started to desorb phosphate from goethite just by flowing supporting electrolyte at the same pH, at the same temperature, just supporting electrolyte. And we've seen some decrease in the signal here as a function of time. The desorption here is much slower, so we cannot see complete desorption, but we see in the symbols that we have a kind of desorption with the rate that is very slow. So with this kind of experiments, we can measure very well absorption kinetics, desorption kinetics, and lines are model predictions. So our model, if it is very simple, is very good for predicting absorption and desorption. Now I'm going to show you a slide about the model we're using. We are not going into the equation. This is a kinetic model. It's a very classic model. When we have an interface, we have to combine transport, and we have to combine it with surface reaction, attachment and detachment. So we have a solution, an homogeneous solution, for example, with phosphate. Phosphate from the solution bowl has to be transported towards the surface, and once phosphate arrives to the surface, it has to attach to the surface group or detach from the surface group. So in this equation, the only thing we're going to see is just absorption or desorption rate, and the parameters we obtain with the experiments are KT. This is a transport constant, so this is telling how fast is transport, and then we get an absorption or an attachment rate constant, so it's telling us how fast phosphate here or the molecule here attach the surface group. And also we have this rate constant, this is desorption rate constant, that is telling us how fast phosphate or the other molecule is detaching from the surface. So with this kind of experiment, we can measure KT, Ka, and Kd, and we get information from that. These are examples for phosphate adsorption on goethite. This is adsorption and desorption. You see, in all cases, desorption is much lower than adsorption. And the only thing we have changed here is the phosphate concentration, 3 to 10 to the minus 6 molar, and we change concentration 100 times, so 3 times to the minus 4 molar. And if we measure the initial adsorption rate here, we're going to see that the rate increased 100 times from here to here. That's telling us that it's first order with respect of phosphate. Again, symbols here are experimental points, and lines are model predictions. And model predictions were all done with always the same parameters. The only parameters we need for these predictions, for this modeling, is the attachment rate constant, the detachment rate constant, the transport constant, and then 2 parameters for the equilibrium situation for the adsorption isotherm, because this model can predict perfectly well the adsorption kinetics, the desorption kinetics at all phosphate concentrations, and also the equilibrium situation. This is what the model predicts in the equilibrium situation at very long times. These are experimental points. This is an adsorption isotherms, and lines are model prediction with all these parameters. So the system we are working with is good for determining transport parameters, detachment, and attachment. What we have learned with this, just to begin, we have learned that in this kind of systems with phosphate or glyphosate, it's better to measure desorption rates than measuring absorption rate. And this is an example. Again, these same symbols are experimental data for absorption and desorption. Lines are model predictions, and we can take from this adsorb amount as a function of time. If we take the derivative here from this curve, we get the absorption rate, or the derivative here, we get the desorption rate. So we can experimental adsorption rate. This is at 100 time, adsorption rate as a function of the adsorbed amount. And symbols are experimental data, and this is the model prediction for the mixed transport and reaction. What is nice here is that we can compare the experimental data with the model prediction for pure transport control and for pure reaction control. And what we see here is that in the case of adsorption, this part here is for adsorption, is here. In the case of adsorption, the process, the adsorption rate is controlled by transport. So we cannot say much about attachment rate or desorption rate, because the only thing we can get accurately is the transport constant. in this case, adsorption is not very good for measuring the rate parameters. But if we go to desorption is very slow, is much slower than the transport. So what is controlling the rate here is the desorption. And if we compare here with the model prediction, so these are the experimental data. This is transport control for desorption. This is reaction control. And we see that our experimental data coincide with reaction control, so that measuring the desorption rate directly gives us rate constant. And with that, we can obtain, let me go backwards, with that we can get desorption detachment rate constant, and also with the help of the adsorption isotherm attachment rate constant. So having this in mind, we started to study desorption rate of glyphosate from goethite. So it is much better studying desorption than studying absorption in this kind of systems. And before going to the results, we need to come back to the mechanism of the ligand exchange reaction. Remember you that there were two limiting cases, dissociative substitution, and as I told you, in dissociative substitution, this is the rate determining step, and the entering ligand is not participating in this step. So if we change the ligand, the reaction rate won't change much, because the reaction rate is controlled by the breaking of this bond here between the metal ion and the living ligand. In this case, if the mechanism is dissociative substitution, we are going to see a weak or no dependence of rate on the nature of the entering ligand. And this is a typical example for substitution of nickel complex in solution. Look at this. This has been done 50 years ago, so this is very well known in solution. This is just a reaction when one water molecule, one ligand here is being substituted by one entering ligand. And these people here have used different entering ligands: sulfate, acetate, thiocyanate, fluoride, water, ammonia, pyridine, and they measure the reaction rate. We have the rate constant here, but it's better to see the logarithm of the rate constant. It's 4.2, 4.5, 3.8, everything around 4. This is typical for dissociative substitution. There are some differences in the rate constant, but they are all within the same order of magnitude. So there is a weak dependence of rate on the nature of the entering ligand. Let's see what happened with the living ligand, with the associative substitution. The rate determining step is this one, and the entering ligand is participating in this reaction. So we expect a strong dependence of rate on the nature of the entering ligand. And this is a typical example for a chromium complex. This is the entering ligand, and they have changed these 4 ligands, and you see the rate constant or the logarithm. These are here, this is around -6, and this is -9. So there are 3 orders of magnitude of difference. Here, the reaction rate is changing 1,000 times by changing this ligand or changing or using this ligand here. So there's a strong dependence of the rate on the nature of the entering ligand. So this is a good tool to just to try to study the mechanism of adsorption or desorption of ligand from mineral surfaces. If we find a weak dependence, it should be this kind of mechanism, and if we found a strong dependence with the nature of the entering ligand, we're going to have, or we can say that we have a kind of associative substitution. What we have done is to study the desorption mechanism of glyphosate from goethite. We have adsorbed first glyphosate to goethite, and this should be the desorption reaction. We have glyphosate attached to the cation at the surface of goethite, and then we added an entering ligand, this white here, and then we we displaced the entering ligand. We displaced this glyphosate is going to act as a leaving ligand, and this is going to act as an entering ligand to have this as the reaction product. So if we change the nature of Y and we study the rate of this desorption reaction, we can tell something about the desorption mechanism of glyphosate. And what we have done is to study different entering ligands, just water, washing with water, using phosphate, sulfate, carbonate, citrate, oxalate, anything we could get in the laboratory that could act as good ligand for iron-3 at the surface of goethite, we have used and we have tried to see what happened with the desorption rate of glyphosate. And for that, we have done experiments with ATR, FTIR spectroscopy. This is an example of what we get when we use phosphate to dissolve glyphosate. This is the first part, glyphosate adsorption. First, we flow glyphosate, and we have that glyphosate signals, the bands of glyphosate are growing on time. So this is telling that glyphosate is adsorbing at the goethite surface. Then we switch to a phosphate solution just to dissolve glyphosate, and what we see is that the signal, the bands of glyphosate decrease on time, and the bands of phosphate increase on time. This is telling us that glyphosate is being dissolved and phosphate is being absorbed. So this is a typical ligand exchange or ligand substitution process. If we plot adsorbed glyphosate as a function of time from this data, where at the beginning we have the adsorption, and then when we added phosphate, we have glyphosate desorption. And we have tried different concentration of phosphate. We have changed 4 orders of magnitude, 10 to the minus 6, 10 to the minus 2 molar phosphate. These concentrations here are more than enough to completely saturate the surface and completely displace glyphosate from the surface. And we don't see significant changes. This is more experimental error than real changes. These are all data here, all rates here are all within the same order of magnitude. This means that is of 0 order respect of the entering ligand, respect of phosphate in this case. And then, well, from this data, we got the detachment rate constant, and we compare this detachment rate constant with the rate constant obtained with different entering ligands. Those were the data for phosphate, and then if we use oxalate, we have this. If we use EDTA, this, citrate, sulfate, etc., etc. Anything we use as an entering ligand, they gave more or less always the same desorption rate. We can have here a table with the desorption rate constant for different entering ligands, and you see that they are all within the same order of magnitude. So there is not much dependency of the rate on the nature of the entering ligand. So this is quite typical of a kind of dissociative mechanism. I'm going backwards. That means that for glyphosate, it doesn't matter what is used as entering ligand. What is controlling the reaction rate is the breaking of this bond here. So this breaking the bond is leaving a free room, and then in a second or in another step, the entering ligand is coming to attach iron and to get adsorbed instead of glyphosate. But the rate determining step seems to be this bond breaking here. This has quite important environmental implications. This is saying that the desorption rate of glyphosate will be always the same, irrespective of the substance that displaces it from the surface. This is highly important to predict the mobility of glyphosate in the environment. Glyphosate, you know, is an herbicide that is heavily used here in Argentina, even more in Brazil and the USA. So it is good to be able to predict the mobility of glyphosate in soils and nature and natural waters. And the prediction is going to be quite easy because, well, the mobility doesn't depend on the substance that is used to displace it, because the rate controlling step is just the breaking of the bond between glyphosate and the iron-3 that is located at the surface of goethite. This is, then we can speak more about this if you want. Just I want to tell you something about materials that we are using for decontamination, or we want to use for, we study for decontamination or decontamination of aqua solution, just to clean aqua solution. We usually look for good adsorbents. We try to study materials that are good adsorbent. We are specialists in adsorption desorption processes, so we are looking for adsorbents, and we're looking for good adsorbents. Then we are going to see what we mean with good adsorbent. We are looking also for cheap adsorbents. If we want to decontaminate a lake or a river or a natural water somewhere, we need to use a lot of it. We need to use a lot of adsorbent, so it has to be cheap. And if we are going to use them in nature, they have to be green. We cannot make a synthetic adsorbent with a lot of contaminating molecules, because we won't be able to use them in nature. So we look also for green adsorbent. And the adsorbents, or the substances that meet all these conditions, are minerals. Minerals or synthetic minerals. Minerals are inorganic solids that are made by nature. So they already exist in nature, and if we use them and we pour them in nature, so they are not going to contaminate nature. This is just adding nature to nature. Is not going to contaminate, but we can clean some aqua solution. We can clean some, I don't know, we can use it for cleaning rivers or for cleaning lakes or that kind of thing. The minerals we are studying are clays. Clays are very good for cationic pollutants. We are also studying layered double hydroxide, hydrotalcite. This is the name of the minerals. These are good for anionic pollutants, negatively charged pollutants, positively charged pollutants. Iron oxides are everywhere in nature, so they are not going to contaminate nature, and they are very active. They are good for ligands like phosphate, glyphosate, good for arsenate, and we are also studying mesoporous silicon dioxide. Silicon dioxide is just the sand you have in all your beaches, so it is not contaminated. The only problem with this mesoporous material is that to prepare them, we may need extra chemicals, or sometimes to make it more reactive towards different substances, we have to modify the surface, so they may be not so green. But if we use just silicon dioxide, this is really good also because they have a high surface area, so they are going to be good adsorbent. So what we mean, I have this one here. We are using lately mixtures of these things here. For example, we can mix clays that are good for cations, for absorbing cations, and we mix them with iron oxide with magnetite. This magnetite is good for absorbing arsenate or for absorbing glyphosate, absorbing phosphate, and when we combine them, we impart to these clays magnetic properties. So with magnetic particles, we can remove them quite easily with a magnet. So this is quite convenient for decontaminating aqueous solutions. What we mean with good adsorbent? Here we have some examples. I hope you can see this figure. These are data for arsenic adsorption on different solids that were proposed in the literature to act as good adsorbent for arsenic. This is a ferrihydride. This is iron hydroxide at pH 4.5. This is very good. What we plot here is an adsorption isotherm. This is adsorbed amount as a function of the equilibrium concentration. Ferrihydride adsorbs a lot at pH 4.5. arsenic. This is the same ferrihydride at higher pH, at pH 9, is still good adsorbent. LDA, this is a layer double hydroxide, is if we compare this data here with this data here, this is much better adsorbent than the other one, and these ones are not good adsorbents. But not always we have to see the amount that it's adsorbed here. Just compare this one that seems to be better adsorbent than this ferrihydride here, and we have that in this figure. This is the LDH data, and the lines are the Langmuir isotherm just to fit the experimental data, and this is the case for ferrihydride. The Langmuir isotherm is telling that the maximum adsorbing capacity of LDH is 2,000 micromole per grams, and for ferrihydride is 1,000. So this is the maximum adsorption capacity of this one is twice as much as the maximum adsorption capacity of this one. But we shouldn't look at the maximum adsorption capacity, because the maximum adsorption capacity occurs at very high concentration in solution. You have to remember that this is an adsorption isotherms, and we are plotting here adsorbed amount as a function of the equilibrium concentration that is left in the solution. So if we want that this solid here absorb this high amount of arsenic, once this high amount of arsenic is in equilibrium with this concentration in solution. So once we take out or we withdraw the solid from the solution, the concentration left in the aqueous solution is this one. And for arsenic, this concentration is extremely high. We cannot drink water with this arsenic concentration because it's really, really toxic. In that case, ferrihydride is much better. It will absorb less for the same amount of solid, but the concentration that is left in solution is much lower. So this is much better adsorbent, this one here, than this one here, if we want to purify an aqueous solution containing arsenic. This is well seen in a semi-logarithmic scale. We have a semi-logarithmic scale here. These are the same data and the same line and model predictions, and you can see that LDH is very good adsorbent at very high concentration, but at concentration levels that are close to safe level for arsenic in water, it is not good adsorbent at all. And we want that the solid be a good adsorbent at these levels. In this case, ferrihydride is much better. And if we put ferrihydride at these levels here, it still will absorb and will decontaminate water with arsenic. This one is not going to be a good adsorbent in this case. And as the last example, sometimes we need good adsorbents that is good adsorbent under certain conditions and very bad adsorbent under other conditions. And this is the case of iron oxides or magnetite. This is the example of magnetite. This is adsorption of arsenic at different pH by this iron oxide magnetite. At pH 4, it's very good adsorbent. So it takes a lot of arsenic. It will decontaminate a solution without any problem. But at pH 11, is a very bad adsorbent. In this case, this can be used very well in analytical chemistry, for example. If we want to detect and we want to measure the concentration of an arsenic solution, for example, with this kind of system, we have our arsenic solution, a very diluted one. So this concentration here, maybe the detector cannot see this concentration because it's very diluted. So what we do is just to flow, to put pH 4 here, to change the pH to 4, and to flow this arsenic solution through a column with magnetite at pH 4. At pH 4, magnetite is going to absorb a lot of arsenic. Arsenic is going to concentrate here, and then when it's very concentrated at the surface of the mineral, we change the pH. We change the pH to 11. So when the pH 11 is here, everything will be dissolved, and all arsenic that was pre-concentrated here will be dissolved all together, so will be very concentrated here, and in this case the detector can see that concentration. So it's good in analytical chemistry, that kind of system. We can, because we can use easily those systems as pre-concentration solids. So let me see. This is more or less all what I wanted to tell you. The main conclusion when we do a mineral metal oxides is that it is very useful to make analogies between reaction in solution and reaction at the surface. If we know how a metal reacts in solution, well, we can learn quite a lot from that about how react that metal at the surface of a mineral or the surface of a metal oxide. Let me show you just before finishing my talk. This is part of the group. This is what actually there are two groups here. This is pre-pandemic picture, so we could be all together, and this is kind of pandemic picture when we meet all together as you do now via internet, via Google Meet, and also some collaborations. We are working usually with Chinese people and Dutch people from Holland, from the Netherlands. This was my mentor when I did a postdoc in the Netherlands. He's already retired, but he's still very active. So we keep in touch, and we still publish together. And with Wenfeng Tang, well, this is a very powerful professor in China. They have a lot of money, they have a lot of equipment, so we use spectroscopies with them. We can go to the synchrotron to see absorption. And look here, this is from Wuhan, so I'm prohibited. We cannot go to Wuhan nowadays, but we expect next year or in the coming year to go back to Wuhan and to continue our collaboration. So I think this is all. Thank you for staying there, and I hope you have liked the talk I'm giving to you.
Okay, thank you very much, Marcelo, for your very nice talk. If I don't know how do you want to do, if you read the question of the student or I read for you. You can see them, all the question in the chat of the...
Where is it? How many questions?
So the first one is from Felipe
Machado. Maybe you act as a moderator. That may be...
So the first one from Felipe is how can the multiple balance of the metal affect the kinetic mechanism of the reaction and the phenomena of adsorption-desorption on catalytic surface?
Well, yeah, they can affect quite a lot. We were studying very simple system just to learn about the system and to obtain rate constant. But if you have different metals in solution, or you have different ligands in solution, or you have a mix of minerals or oxide, they compete all together. They compete for surface side, and they are competing. This is just a kind of well, you can sometimes you can follow the competition as I shown you with the ATR when I added phosphate, that you start seeing the signal of phosphate and the signal of glyphosate that decrease. This is competition for surface side. So the higher the amount of metals and ligands you have in solution, they will compete and they will affect, of course, the kinetics. The mechanism may be more or less the same, but they will compete and they will affect the kinetics. In your modeling, you have to consider all species competing all together.
So the second one is related to the model. He asked what represents theta in your, when you make the...
Oh, this is the surface coverage. This is the surface coverage. So theta equal to 1 is 100% of the surface covered with that substance. theta is 0.5 is 50%. This is you can calculate it quite easily from the adsorbed amount divided the maximum capacity for absorption. Theta is the surface coverage. So from 0 to 1 it goes from 0 to 100% of surface coverage. So just with the factor you can convert from theta to rate without any problem.
So the other question is regarding the study of glyphosate. And she wants to know is what is the impact of this adsorption desertion process of the environmental issues, and if you use a salt of glyphosate, and what kind of salt is of the means you use a potassium salt or ammonium salt?
I don't remember. No, I think it's quite no. It's not a salt. You can get it in Sigma. I don't remember if it is a salt, but no. I think it's protonated. It's in protonated form, so that you don't have cations. And the impact, we do really basic chemistry. We don't go to the environment. These Chinese people, they go to farms and they go to field. They make field study. But we here in Bahia Blanca, we just do basic chemistry. What I can tell you is that it's very important, the competition between glyphosate and phosphate. So glyphosate is used as an herbicide. That's an herbicide. So farmer is applying once or twice a year to the field just as an herbicide. And after 2 or 3 months, they use phosphate because phosphate is a nutrient. It's a fertilizer. So if you go to farm, you first apply glyphosate, and then you apply phosphate and at very high concentration. And then the next year they apply glyphosate again, and then phosphate again. So they are continuously competing for the surface. So this has a really strong, it has to have a really strong effect on the mobility of glyphosate and phosphate, because they are continuously applying the fertilizer and applying the herbicide, and they applied a lot. If you look at the numbers, they applied a lot of herbicide, and they apply even more fertilizer. They apply even more phosphate. So they compete quite a lot. It has a lot of influence because phosphate is displacing glyphosate, and glyphosate is displacing phosphate from the surface.
Okay, the next one is regarding the what kind of isotherm of absorption you use, and how you take the decision that what isotherm is the best for your system.
Yeah, we don't mind much about the kind of isotherm. So the simplest one is Langmuir isotherm. So it has some theoretical basis, so you can understand what is happening. And if you have good prediction or good fitting of data with the Langmuir isotherm, please just use Langmuir isotherm, because you may have another isotherms, but they are quite empirical isotherms, so you don't know what they mean. You are going to get good data fitting, but maybe you don't know what they mean. You just get a nice line that is going through your points, but you cannot interpret it very well. Instead, with the Langmuir isotherm, you know very well what the initial slope of the isotherm means. This is related to the equilibrium constant for adsorption, and you know what it's level of the isotherm, while this is related to the maximum capacity for adsorption. So if you can get a good fitting with the Langmuir isotherm, please use Langmuir isotherm. It's going to simplify your life.
Okay, the next one is money, and is I think that is a quite interesting question. Say, why is different the adsorption process and the desorption process. So why normally the adsorption process is faster than the desorption process?
Well, they are related to the equilibrium constant. In this system, the equilibrium constant is quite high. In an equilibrium constant, the equilibrium constant is just the ratio between the attachment rate constant divided the detachment rate constant. So that ratio has to be high. That means that attachment is much higher than detachment. And it's when you have a molecule that has a high affinity for the surface, so it's going to absorb quickly, but then it's going to be retained at the surface quite a lot. So it's going to dissolve quite slowly. That depends on the affinity of the molecule or the ion for the surface. The higher the affinity for the surface, the higher the equilibrium constant, the faster is the absorption and the slower is the desorption. And this is just because of the ratio between the absorption rate divided the desorption rate. That has to give the equilibrium constant. I don't know if I explain myself.
Okay, so now I need some seconds to see because it's a very long question from Leonardo.
Good. Nice to see that you ask a lot.
Well, the first question is if the mechanism and the associative substitution depends from the properties of the ligand and the adsorption molecule, means L and Epsilon.
Yeah, depends on both of the complex and the entering ligand. It depends of both. And what happens is that I told you about two limiting cases, just dissociative substitution, that is one extreme, and associative substitution is the other extreme. We have a whole family between associative and dissociative. So I've shown you that there are two very differentiated steps in both cases, but in most of the cases, it's something intermediate. When one ligand is entering, you can see my hands or not?
Yeah.
Can you see my? So when one ligand is entering, the other one is leaving, and this is called interchange. So it's a kind of concerted process. So I just to make it simpler, I just told you about the two extremes, the dissociative and the associative mechanism, but there's a whole family of intermediate mechanisms that are called interchange. And they say, well, if this interchange is similar to associative, this is called associative interchange. And if this interchange closer to be dissociated, this is called dissociative interchange. So you have a whole family where maybe the effect of the entering ligand is really strong, and in other cases is not strong at all, so it doesn't exist at all, but you have also intermediate behavior. So it depends on the entering ligand. It may depend on the leaving ligand and also on the metal cation. There are metal ions that are really inert and they don't like to exchange, so they go really slowly. And there are metal cations that are really labile, so they exchange them quite quickly. It depends on everything. Yeah.
Okay. The second question is related to the other one, not this one, but the other person. Is related to, for example, in the case of phosphate desorption rate, that is very small compared with the adsorption rate, and if this does not change with the concentration, and if this means that the reaction kinetic is control all the process and there are no influence of the transport in solution.
Yeah, for the desorption is phosphate desorption or glyphosate desorption is very fast as compared to transport. So if we measure desorption, we are almost sure in this system that we are measuring the rate constant. I didn't tell you, but we need to have in mind that if we are working in an aqueous solution, we have theoretically two processes that are going in parallel, because you have phosphate that is acting as an entering ligand to displace glyphosate, but we also have water because it's an aqueous solution, and water is a good ligand. So water is also acting as a ligand. So there are two processes in parallel. Glyphosate is being displaced by water, and the concentration of water is really high in an aqueous solution. And the other part of the process is glyphosate being displaced by phosphate. So I think when we use a very low concentrated phosphate solution, the main thing we see is just replacement of glyphosate by water mainly, because phosphate was really, the concentration of phosphate was really low. At the higher concentration of phosphate, we think that phosphate is really acting as the entering ligand, and the main process is the one that is going through phosphate as entering ligand and glyphosate as leaving ligand. But in all cases, the rate was more or less the same. So being water or being phosphate as the displacing ligand, the rate were more or less the same. So that means that everything depends on the breaking of the bond between iron and glyphosate.
Okay, Leonardo, I think that he respond also the third question. So I go directly to the fourth question of Leonardo, is regarding the arsenic absorption. How, from the chemical point of view, why is so affected by the change in pH? And if this change in pH is related to the change of magnetic surface, or
it's changing to both. So arsenic, you have arsenate. Arsenate is changing speciation if you change pH. So if you are a low pH, you have protonated arsenate. So this may be monoprotonated or biprotonated. And if you increase the pH, you will have arsenate, so completely deprotonated. So you have different things here. And the surface of magnetite and the surface of oxide is also changing because the surface is becoming deprotonated as you increase the pH. So you have the magnetite surface that is becoming deprotonated, and the surface charge, you have an electrical charge at the surface that is changing from positive at low pH to negative at high pH. Yeah, the isoelectric point of magnetite is around 6 or 7. So at pH lower than 6 or 7, the net surface charge is positive, and at pH higher than 7, the net surface charge is negative. And then you have also arsenate that is changing charges. You have a -1 charge at low pH and -3 charge of the anion at high pH. So you have a lot of electrical repulsion. If you increase the pH, you have a lot of electrical repulsion that is driving the desorption or this decreasing the absorption. If you are at pH 11, for example, you are going to have a negatively charged surface and a triply negatively charged arsenate ion. So the interaction there is not good at all, so it won't absorb. If you go to low pH, positive charge with a negative charge ion, they will absorb. So this is the electrostatic part. Then there is a chemical interaction also that influences, but the electrostatic part explains why if you increase the pH, the interaction should decrease.
Okay, the next one, Tiago. He would like to know how do you make the mixture of the adsorbent material? If it's only a physical mixture, or you work also with more sophisticated things, making reaction to combine these materials?
No, we try to do it as simple as possible. And with clays and with magnetite, it's just a physical mixture. We have a dispersion of clay, monomerilonite we use, and a suspension of magnetite, and we just mix them, and they aggregate, they make co-aggregates. I don't know how to call them, but they mix, and they act perfectly. So the clay is going to absorb cations, and magnetite is going to absorb anions and phosphate and glyphosate. And the nice thing is that if you apply a magnet and everything goes together. So the clay, if you have pure clay and you apply a magnet and you use a magnet, you cannot remove it. But if you mix it, just a physical mixture with magnetite, it will be covered. I don't know what happens there. So they coagulate together. So all aggregates are becoming magnetized. So when you apply the magnet, you remove everything and you get a really clean solution. We try to make them as simple as possible. Of course, if you add polymers or you add some molecules, you can make those aggregates more stable. But in this way already, we can get a clean solution just by mixing them. It's a physical mixture.
The next one, Diana would like to know if you can do this desorption, absorption, kinetic by ATR, how do you do, in heterogeneous and non-static medium. I think that this is the way that you did.
Non-static, yeah, this was kinetic. But yeah, you can do it heterogeneous system. The problem of ATR, FTIR spectroscopy is that we're working with aqueous solution. The main problem is that we are working with aqueous solution. And the window, the infrared window we have to see our molecules or to see our ions is really small. So we cannot see many things. We cannot see arsenic, for example. We can see the vibration of phosphate. We can see the vibration of glyphosate. We could see the vibration of carbonate and carboxylate groups, but we cannot see arsenic. So in this way, we need to use a different system, or we need to change to a non-aqueous solvent. So we cannot do that. That's the main problem of infrared. We have a very small window, infrared window, to see our species. But if we can see them, it's really easy to work with.
Okay, I think that is the next question made by William. You have given your response just now, because it's also related with different setup experiment and different kind of material. So the problem is water, and mainly water.
The main problem is water. The main problem is water. So you cannot see anything you want to see. So you have to select your system, and you have to work with the system is detecting your infrared. So we were lucky with phosphate and glyphosate. Well, glyphosate has a phosphonate group, so it appears in a very close region to the bands of phosphate, so we can follow them. But arsenic, we try to do that, and no way with goethite. Perhaps if you change, instead of goethite, you change to aluminum oxide or silicon oxide, perhaps the vibration there you can see, but not iron phosphorus. You cannot see that vibration. So if you want, I have a 1 minute video just to show how a physical mixture of clay and magnetite work for us as an absorbent. Let me try. Can I do that?
Yeah, of course.
Good.
Leandro, can do that?
Good. Let me see if Can you see this?
Yeah.
Good. So this is not very well seen here, but let me show you. This is a test tube. So this is the glass. This is a glass tube. This is a test tube, and we are going to add a blue pollutant. This is methylene blue, and then we're going to add our mixture of clay. So this is methylene blue that we have added. I'm going to do it quicker. This is methylene blue. This is in Spanish, so you understand well. No problem. I'm going quicker. So we move it to homogenize the solution, and then we add the dispersion. Let me go backwards a little bit. So this is a dispersion. This is a physical mixture of a clay, montmorillonite, and magnetite, and we add a few milliliters to this solution here. So the methylene blue is going to be adsorbed. Methylene blue is going to be adsorbed on the clay, and then when we apply the magnet, so now it's just moving a little bit just to homogenize it. Yeah, it's homogenizing it. We wait just for a few seconds for the reaction to take place, and then we apply a magnet. Now, the magnet is being applied. And you can see that the clay and magnetite, all is being attracted by the magnet. So we have cleaned that solution quite easily, just with a really physical mixture of a clay and magnetite. So we don't need to make special reactions between the oxide and the clay just to make it aggregated. You can clean them quite easily. We are trying to study how those aggregates are formed, but what we can see is that, yeah, you can attract everything, even though clay is not attracted by the magnet.
Okay, we are going to the last question from the student, and Abrar would like to know how the thermal change, like exothermic or endothermic phenomenon in absorption, desorption, how is related, and if all the absorption process are, I don't know, exothermic and endothermic, or it depends of the material that you use?
It depends it depends on the material. If you are in the gas-solid interface, usually they are exothermic. But in the solid-liquid interface, this is an exchange. The reaction we have shown is an exchange reaction. So it depends on the breaking of a bond and the formation of a second bond. So it can be exothermic, or delta H can be close to zero. That depends on the system. And of course, kinetic is going to increase, in all cases, if you increase the temperature. That's another problem of infrared with aqueous solution. We cannot change much the temperature. We don't have a setup just to change the temperature of our solution. Maybe we can work with between 10 degrees and 40 degrees just to see how the kinetic changes. But yeah, it would have been nice to have studied the system at the larger temperature, delta T. But yeah, if you increase the temperature, kinetic is going to increase.
Well, we have a last minute question from the student, is if you can reuse the absorbent material, means the magnetite and the clay.
Yeah, it depends on the system. If you use magnetite for absorbing arsenic, yeah, you absorb arsenic at pH 4, and then you wash it at pH 11, and then you have a clean surface again. You can reuse it. In that case, there's no problem. With the case of the methylene blue, the blue the blue solution with the clay, no, the affinity is so high there that once it goes to the surface, you cannot get it out. I mean, it depends on the system. Of course, it's better to have system that you can reuse. The case of arsenic and magnetite, yeah, you can reuse it many times.
Okay. Leandro, do you have some question from the YouTube guys? No. Okay. Vera, Mauro, Leandro, do you have some question that do you want to?
Ladies first.
Il microfono, Vera.
Marcelo, thank you for this so nice and clear presentation. And this is a subject that I like very much because I work also with minerals. Yeah. Yes. And I would like to know about the interactions between the molecules and the minerals, because I understood that you have considering the formation of metal complex, but also you have considered the zeta potential of these particles. Yeah.
Oh, yeah. The electrostatic interaction is very important. So what I showed you is a kind of chemical interaction. They really form a chemical bond. So this is a chemical bond between the cation, iron 3 in this case, with the ligand. But this chemical bond will be increased if there is an electrostatic attraction between the surface, and then there is an electrostatic attraction between the surface and the absorbing ion. For example, if you are absorbing an ion as arsenate, it's going to absorb better at low pH, where the zeta potential is positive of the surface. You have a positive zeta potential. That means that you have a positively charged surface. It will attract better arsenate than if you are at pH 10 or 11, where the zeta potential is negative. So that a negative zeta potential means that surface is negatively charged, so the attraction is not going to be good. You still have the chemical contribution to the binding, but the electrostatic contribution is going to be the other way around. It will try to repel the ion.
Yeah. Can I do other questions?
Of course.
Yeah. Have you used some spectroscopy technique to confirm the coordination of the molecules to the mineral surface? Because
we didn't do that. We did something with phosphate on goethite, and to confirm the coordination is better to do not infrared, but to do synchrotron, spectroscopy, X-ray absorption, X-ains, and X-subs, and we haven't done that much, but there are many works, there are many publications in the literature where they have studied phosphate and arsenic absorption on metal oxides, mainly on aluminum oxides and iron oxide, and they confirm that kind of coordination. There's still under discussion with phosphate, if phosphate is going just monodentate
or bidentate.
There's a huge discussion in the literature that they don't know it very well, but that you can see the coordination quite well with synchrotron-based spectroscopy.
Okay, and when you work with smectites like montmorillonite, have you seen delamination or something like this?
Yeah, montmorillonite delaminates if you don't have divalent cations. I mean, if you are in a sodium chloride solution and if you are not at low pH, more or less delaminate. But if you add some calcium or you add some divalent cations, I don't know, or iron 3, is going to go within the within the layers, and you're going to
With
have
the stacking.
Yeah, you're going to have a stacking. Well, you could see in the video that once we added more morillonite, so the dispersion at the beginning was really, I don't know if delaminated, but it was a kind of homogeneous dispersion. But once methylene blue went into the layers, in the interlayer space of more morillonite, it just aggregate all together. Yeah.
Oh, okay.
Yeah, if you have potassium or you have sodium just as the only cations, morillonite will tend to delaminate. As soon as you add divalent cations, it will stack.
Okay. And the surface area is very important in your experiments, yeah? And I guess that you are not using a natural layer double hydroxide. So I would like to ask about the synthesis. Have you some strategy to get a high surface area?
No, we are using them mainly. Well, the examples I've shown you were mainly for arsenic adsorption, but we are using them mainly with pharmaceutical products, just for using them as a drug delivery system. And we normally use the three methodologies you have. This is co-precipitation. I don't remember the name of the three methods for preparing them, and we use those three methods and then try to compare which works better. But I don't know, for high surface area, we never try to get to check the surface area. But
Okay.
yeah, it depends on how they stack also. So if they delaminate, you will have a really high surface area, around 1,000 square meters per gram, if you have it completely delaminated. But if you have it stacked, so you have just the external surface, and then the surface area is going to be much lower. But we haven't investigated the effect of synthesis method on the surface area.
Okay.
Yeah. If you have done something,
excuse me?
If you have done something about that, please send me some articles about it.
Yeah, okay. We can talk. And I have the last question is about the possibility to use Raman spectroscopy to do these experiments, because minerals have a very low intensity signal in Raman. Or it's not possible?
Yeah, I think Raman is going to be a good spectroscopy, but I'm not specialist in Raman at all. We don't have it in our university. So I would like to do something with Raman spectroscopy, and I think it's going to be very useful for that. Yeah, but
yes, I think that's possible.
I have no experience in that.
Oh yeah, I think that you can use a laser in your setup. Yeah, and maybe you have a more clean region to monitor.
Yeah.
The molecules.
You're right. The main problem is that we don't have it in Bahia Blanca. We don't have the equipment. We're trying to buy one, and I think it's going to be very useful. Maybe not for phosphate or glyphosate,
yes,
but for sure you can use it with other systems. Yeah, you're right.
Okay, it's this. Thank you very much.
Thank you.
Mauro?
Marcelo, thank you very much for your very nice presentation. Thank you.
Okay, thank you. I hope you understood.
Yes,
well,
everything.
This is an English presentation. I go slowly because
it was very nice.
So I think you may have understood my English.
I have just one question.
Yeah.
It seems that the adsorption process is mass transport control, but the adsorption depends on the kinetics. Can you make a comment on the influence of flow rate on both absorption and desorption?
In this case, in the cases we are working with, well, flow rate is going to modify quite a lot the absorption rate,
Yes.
because it's transport control.
Yes.
Flow rate is going to modify the absorption rate, but it's not going to modify the distortion rate.
Okay.
We haven't tried, we haven't changed the flow
Yes.
rate, because we have a problem also with when you have the ATR crystal, we have to make to deposit a layer of a film of our particles.
Mm-hmm.
And if we increase a lot our flow rate, it will remove all our particles. So the best way of studying changes in flow rate is just to try to stick somehow the film to the crystal. So if you increase the rate, so you don't remove the particles. But in our case, if we increase the flow rate, particles are going out, so we can't start. So it's just a kind of compromise.
Yes, I understood. I think in the one of the last slides, you showed that it's possible to detect arsenium by pre-concentration. Have you tried to do that?
I mean, not detection with the infrared.
No.
Here in Bahia Blanca, analytical chemists are good in flow systems.
Okay.
So they are good in flow. So they work with the FIA, FIA. They work with that, and they're really good. They work with column, with pre-concentration columns. So they change flows and they make reaction. I think that for arsenic they use just a colorimetric reaction.
Okay.
They use a colorimetric reaction and they detect arsenic with the UV visible spectrometry.
So you pre-concentrate at pH 4, then
for example, that's
11 you can remove.
That could be used in that way. You pre-concentrate it at pH 4, and then
at pH 11
you change pH 11 and it removes. The main problem may be that if the remotion is slow.
Yeah, that's a problem. That's my question.
So you have to work with different systems to get a system where the remotion is fast.
Yes, it has to be fast.
If you remove it fast, it goes all arsenic together. It will concentrate the solution, so you'll detect it well. But if the distortion is really slow, you'll get just a slow distortion, and you'll get.
That's not going to work.
Yeah.
Yes. Yeah. Okay. Thank you very much.
Thank you.
Leandro.
Thank you, Marcelo, for the lecture. I have two questions. I was thinking about a clean soil before adding glyphosate, for example. What kind of ligands we can find in iron from nature, for example?
In the soil?
Yes. Well,
the main ligand for mineral surfaces are humic acids and fulvic acids. So that's organic matter, humus. I don't know how you call this. This is organic matter, so organic matter. So this is a kind of polyelectrolyte. It has a lot of binding points. It will attach quite strongly to iron oxides. And then you have a lot of chloride, of course. You have sulfate. You have carbonate, quite a lot of carbonate.
Okay.
And phosphate also. Phosphate. Phosphate is not it's not toxic. Phosphate is food. Phosphate is a fertilizer and it's food, and it's food for microorganisms and it's food for plants. And the problem with phosphate, when there are a lot of phosphates in soils, is that they move to lakes. And it's food for algae and for microorganisms. So that you have algae blooms, you have a contamination of lakes because of a lot of algae. I don't know.
Okay.
How you pronounce it.
So maybe you will have.
It's just the opposite. It's food. So you get a growth of microorganisms everywhere because there's plenty of food.
Okay, maybe the main composition would be iron and polyalcohols, something like that, attached to the iron.
In a soil system.
Yes. Okay. Yeah. And the other,
you have
I was thinking about
chloride, sulfate, and carbonate, of course.
Okay. I was thinking about this question because I don't know if did you make any competition studies using free iron and different ligands before adding the glyphosate, or you can study separately and then mixture all together and see if you had some kind of competition or something like that.
With iron in solution?
Yes.
Yeah, no, we haven't done that, but it's a good idea. Yeah,
because
it's a good idea. I think
you showed
with iron in solution, I think ligands are going to iron in solution, so for sure you will have a competition.
Yeah.
And in solution, it goes fast. The reaction with iron in solution, it goes quite fast. So you mix the ligand with iron 3, the reaction is quite fast. I think it's much faster than at the surface. We're investigating also that, because we may have also some diffusion problems within the film. That may be also a problem in our systems.
I'm putting this question because I was thinking about the competition, for example, with inorganic phosphate, with glyphosate, which is an organic phosphate containing a carboxylic acid, correct? So maybe this carboxylic acid can have some good influence in this ligand. And you could use, for example, a simple organic phosphate, and making all these competition studies. Maybe you can try to find some ligand that can have a good competition with iron and glyphosate.
Yeah, but I didn't understand very well your question. What you mean?
For example, if you know which phosphate ligand that you have that is the best kinetics for the ligand for the reaction, maybe you can find another organic phosphate which can have a good competition with iron, and maybe because I was seeing.
There are in nature and in soils other organic, different phosphate. The organic phosphates, they are synthesized by plants, and plants just liberate them to the soil solution. But the concentration of those organic phosphate is much higher, it's much lower, smaller than the real phosphate that is used as a fertilizer. So they are not going to compete. If they are at the same concentration, for sure, that they are going to compete with phosphate and with glyphosate. But the concentration nature of those organic phosphates is much smaller than the concentration of phosphate and glyphosate. So nature, they are not going to compete much, I think.
Yes, but I was thinking about your proposition. For example, if you want to remove the glyphosate from nature, from the iron, so maybe you can have another organic phosphate that you can replace this. And I was thinking about this because.
But you should look for an organic phosphate that is not a contaminant, it's not a pollutant,
correct.
And something that then degrades into something that is not a pollutant. You could look.
Correct.
We have started to study another herbicide, which we are just starting. This is glufosinate. It is very similar. Glufosinate, and it's similar to glyphosate. Is starting to be used here in Argentina as an herbicide. Also, it has a phosphonic group. And this is an organic phosphate. And they say it's less toxic than glyphosate. I don't know. They have just started to do that. Those organic phosphates, of course. If you have an organic molecule with a phosphonic group, for sure it's going to compete with phosphate and with glyphosate. Yeah.
Okay. Thank you, Marcelo. Thank you, Roberto.
Okay, Marcelo, thank you very much.
Thank you.
I have no question because all the questions that I written here, was already discussed. So doesn't make sense to repeat all the game.
If they ask a lot, it's because they understood what I said. So I'm happy. I'm happy.
Okay, so Thank you very much for your talk. Many people in the chat may said that it was a very nice talk, very clear and very didactic. So
I try to do it like that.
I
That's the way I learn it.
Yeah,
That's the way
yeah.
I learn it, just to do it slowly and to try to do it very dynamic.
So thank you very much for your contribution, and I hope that when in some years, because we have a very strict control regarding the people that give talk here, you come again to give a talk. Thank you very much, Marcelo.
Yeah. We're waiting for that, and I hope to have new data to show you.
Yeah,
Thank you.
correct.
I hope to be able to go to the laboratory to get new data.
Marcelo, can you stay here
Yeah.
to talk with me after
Yeah, no
all
problem.
finish? Okay.
No problem at all.
So, thank you very
Bye-bye.
much.
Ciao.
Bye bye.
So, all
Thank you.
next Wednesdays. Okay.
Bye-bye.
Yeah.
Bye.
Okay. Bye bye.
Bien, ciao, bye.